Hello everyone. Today we are going to interpret, understand, and we are going to delve deeper into point collocation method. So grab on your today's cup of coffee and sip on today's mechanical engineering insights. So before we get straight into the business of interpreting point collocation method, these are the steps that we followed to solve the problem of a simply supported beam that is subjected to uniformly distributed load. The first step is to assume a trial solution. So what is the trial solution that you assumed? Well, the type of trial solution that you assumed is a trigonometric trial solution. The question here is, why do you want to assume a trigonometric trial solution? Why not assume a polynomial trial solution of order 4? Order 4 because the governing differential equation is of the order 4. So the reason for assuming a trigonometric trial solution is because the simply supported beam bends like a sine wave. You see here, the green here resembles a sine wave. So that is one of the reasons why you want to assume a trigonometric trial solution. Okay, that is one of the reasons. The second reason is that this particular trial solution immediately satisfies the boundary condition. So it right away satisfies the boundary condition. That is, when you put x is equal to 0, the value of deflection becomes 0. When you put x is equal to L, the value of deflection becomes 0. Similarly, the bending moment on the left and the right extreme ends becomes 0 with this particular trial solution. So this trial solution is very appealing. It is resonating with us. So that is the reason why I assumed this trial solution. That is step number 2, applying the boundary conditions. We see that the boundary conditions are readily satisfied. The third step is to find d power 4 v by dx power 4. So find the value of d power 4 v by dx power 4. We found that value and we substituted that value in the governing differential equation. So when you substituted the value of d power 4 v by dx power 4, that is where the problem comes. That is where we become not so comfortable, because you are going to get the value of constant in terms of a variable, which is clearly a mathematical violation. So how do you alleviate this mathematical violation? What is that you are going to do in order to alleviate this problem? Well, you have to fix the value for x. X is an arbitrary distance, arbitrary location on the beam. You put a point on the beam and you can tell what is the value of x. If you put the point at the center, the value of x is L by 2. So you can substitute a value for x as L by 2, or you can put the value of x as L by 3. Alternatively, you can put the value of x as L by 4, and you can find the value of the constant a, and you can substitute this value of the constant in the trial solution. So the big question is, what is the value of x that you have to put so that the solution closely resembles the exact solution? So that is the big question here, and that is where we are going to interpret point collocation method. So whether you are going to put x is equal to L by 2, that will get closer to the exact solution, or putting x is equal to L by 3 will get you closer to the exact solution. So I have got a series of graphs that I am going to show you. Here you can see the yellow graph line here. So I will just draw that for you. The curve 1 here, the yellow line here, you see that curve is obtained by putting x is equal to L by 2. See, in this graph, along the x-axis, it represents the axial location on the beam. It represents the normalized axial location on the beam. Along the y-axis, you take the value of the residual along the y-axis. So the first curve, you see the first curve is obtained by putting x is equal to L by 2, and you plot the residual along the y-axis, and you plot the normalized axial location along the x-axis, and the type of curve that you are going to get is this yellow line here. So that is the curve that you are going to get. You see, the residual, which is analogous to error, becomes 0 only at L by 2. For example, in this case, L is equal to 1. So the residual becomes 0 at only one point here. I'm indicating that here at only one point, which is not a big deal, which is not a very good idea. So in curve 2, you put x is equal to L by 3. What happens is L by 3, when L is equal to 1, it becomes 0.33. So you see the residual becomes 0 at x is equal to 0.33. Remember, mathematics doesn't discriminate whether you are reckoning x from the left extreme end or whether you are reckoning x from the right extreme end. So what happens is the value of x becomes 0. The value of residual becomes 0 at 0.33 reckoned from the left extreme end and 0.33 reckoned from the right extreme end. So at 2 points, the value of residual becomes 0, which is actually a good thing. So when you put the value as x is equal to L by 3 and set the residual 0, you are actually making the residual 0 at 2 points. One reckoned from the left extreme end, other reckoned from the right extreme end. You see, similarly, if you can put the value of x as L by 4, and you can see that the residual becomes 0 at 0.25 reckoned from the left hand side and 0.25 reckoned from the right hand side. So I will use this red color once again for you. So 0.25 reckoned from the left extreme end and 0.25 reckoned from the right extreme end. So you see that the value of residual becomes 0 at 2 points. So putting x is equal to L by 2 and making the residual 0 is not a very good idea. The reason is because you are making the residual 0. You will be making the residual 0 at only 1 point. I would like to show you another set of graphs here. You see, in this particular graph, the first curve is obtained by putting the residual 0 at x is equal to L by 2. Here, x-axis, as is the usual case, it is the location, that is an arbitrary distance reckoned from the left-hand side. And the y-axis is the deflection of the beam, that is vertical deflection, transverse deflection of the beam. So curve 1 here is obtained by putting x is equal to L by 2. And curve 2, that is shown as green in color, is obtained by setting the residual 0 at x is equal to L by 3. Curve 3, that is the one that is shown as red in color, that is the important curve. That is an important curve. Curve 3 here, I'm trying my best. This particular curve is very important because this curve is the exact solution. This curve is the exact solution. How do you get the exact solution? You have to assume a triangle solution of polynomial form, that is a0 plus a1x plus a2x squared plus a3x cubed plus a4x raised to the power 4. So you have to assume that solution and you have to solve the problem. You see, if you assume that particular solution, you will not get the residual. So that is the reason why we say that is the exact solution. So that is the exact accurate solution. And the curve 4 is obtained by substituting the value of x as L by 4. So what is our interpretation here? A very nice interpretation. That is, x is equal to which curve you think is very closer to the exact solution. You see, the one on the green, I will just represent that here. And one on the green here. So here, one on the green, which is obtained by substituting x is equal to L over 3. And that goes hand in hand. That goes shoulder to shoulder with the exact solution. So you see the green and the red, they are sort of resonating with one another. So we see that at x is equal to L by 3, that is the best optimum solution for point collocation method. That is the interpretation of point collocation method. Okay, the next question here is, if you want to increase the accuracy of point collocation method even further, what is that you are going to do? So if you want to increase the accuracy of point collocation method even further, the trick that you have to pull is, when you assume a trial solution, so I'll write that here. The trial solution that you assumed is v of x is equal to a sine pi x over L. What you have to do is, if you want to increase the accuracy of point collocation method, what you have to do is you have to assume one more term in the point collocation method, that is a sine 2 pi x over L. Since you are adding one more term, in order to differentiate the constants, you can call this constant as a1, you can call this constant as a2. So in this way, you can set the residual at 2 points. Say for example, you can set the residual 0 at x is equal to L over 3 and also at x is equal to L over 4. So if you are going to set the residual 0 at these 2 points, because of symmetry, you will be making the residual 0 at 4 points, because x is equal to L over 3 measured from the left hand side, the residual is going to become 0, and also when it is measured from the right hand side, it is going to become 0. So there are 2 points already right there. And similarly, x is equal to L over 4 measured from the left extreme end, and also x is equal to L over 4 measured from the right extreme end. So in this way, you will be making the residual 0 at 4 points. Oh, that is a terrible 4. Sorry about that. So I'll write that again. 4 points. You will be making the residual 0 at 4 points. So this is your assignment today. Everyone can take this assignment. So assignment is, you have to solve the problem of a simply supported beam that is subjected to uniformly distributed load. So I will write the question here. Solve the problem of a simply supported beam subjected to UDL by assuming 2 terms in the trial solution. Okay, so you will be assuming a trial solution of the form A1 sine pi x over L plus A2 sine 2 pi x over L. Alternatively, you can also assume a trial solution of the form A1 sine pi x over L plus A3 sine 3 pi x over L. Now you may ask me this question, why do you want to assume sine 3 pi x over by L, and why not sine 2 pi x over by L? Well, it is at your discretion. If you assume 3 pi x over L, and if you want to set the residual 0 at x is equal to L over 3, if you do the problem, and when you substitute the value of x as L over 3, it becomes sine 180 degree, and it becomes conducive for you to solve the problem. So mathematically it becomes very conducive. So you can assume a trial solution of the form A1 sine pi x over L plus A3 sine 3 pi x over by L, 3 pi x over L. So the reason is, when you want to set the residual at x is equal to L over 3, it becomes so conducive for you to solve the mathematics. So either you can solve the problem by assuming this trial solution, or you can solve the problem by assuming this trial solution. Okay, this is point collocation method. So if you want to increase the accuracy of this problem by solving the problems by point collocation method, what you have to do is you have to assume more number of terms in the trial solution. So the question here is, what happens if you keep on adding more number of terms in the trial solution? Well, what happens if you add A1 sine pi x over L plus A2 sine 2 pi x over L plus A3 sine 3 pi x over L. Well, if you assume 3 terms, you have to solve 3 equations. 4 terms, you may have to solve 4 equations simultaneously, remember. So more the number of terms in the trial solution, the problem sort of becomes complex and the equations gets twisted around. So you would not fancy the idea of assuming more number of terms in the trial solution because the problem gets complex. So the question here is, how can I simplify this? How can I reduce the error, that is residual, without assuming more number of terms in the trial solution? So that method of reducing the residual without assuming more number of terms in the trial solution, that will be our next method, that is subdomain collocation method. We will delve deeper into subdomain collocation method in the next video. Thank you all for your patience.